Hey guys, this is Mr. Sal. We're going to look at some exponent properties. Thanks for watching. Don't forget to like, comment, and subscribe. So first off, what is an exponent? As it turns out, math people are extraordinarily lazy. So, if I haven't said this already, we found different ways to do things that we found take a long time and simplified them. So before, what we've seen was something like, well, it doesn't have to be a letter even. We could use a number. Like 5, right? 5 plus 5 plus 5. And while adding is extraordinarily fun as well, doing it like this all the time, if it were to happen all the time, kind of stinks a little bit. So what did they do? They said, well, you got 5. Well, how many 5s do you have? You got this one, 6 of them, right? So that's when they created multiplication. And the world rejoiced because we simplified addition, which was repeated addition, all right? Well, the same thing works for multiplication. After they created multiplication, they found that, well, sometimes you multiply things a lot, like 2, right? 2 times 2 times 2 times 2. And you just multiply a bunch of 2's together like this, and you do that a few times, and you start, well, it makes you kind of cranky, right? So what did they do? They said, we're going to find a way to simplify this. So this would end up being 2 to the power of 1, 2, 3, 4, 5, 6, 7, 8. I should count that. 4, 8. There we go. 2 to the power of 8. Well, this brings up some terminology for us. When we look at exponential form, any number, even in this form, but let's look at it a little bit more applicable. Something like 3, and then the power of 8, like this. I would have used 8. Let's do it 9. The 3 here is what we call the base value. And we will want to remember that because in the next unit we look at logarithms, and the base is actually kind of important right there. The 9 is the exponent, but some people like to call it a power. Okay, so if we say exponent, and then your friend says power, they mean the same thing if we're talking about exponents, okay? However, the base is always just the base on this one. So up here at the top, x is the base, and n is the exponent. And yes, we can have variables in the base or the exponent. All right, so here's our first problem. Write 8 times 8 times 8 times 8 times 8 times 8 times 8 in exponential form. So the base is the value that's being multiplied together over and over and over, which in this case is 8. And the exponent is how many times it was multiplied together. 1, 2, 3, 4, 5, 6, 7. 7 times. 8 to the power of 7, bam. Now this may seem kind of, I don't know, frivolous. However, if we can take this expanded form and change it into exponential form, then the rest of this should actually go pretty easily. So now it wants us to evaluate these. So the last one, it just wanted it in exponential form, so that's a base and an exponent. Evaluation is the actual value of this. So 5 to the power of 3 would be 5 times 5 times 5. And yeah, you could put that into a calculator with the exponent, but we'll cover that later. This is going to be 125. 2 to the power of 5 is 2 times 2 times 2. This is going to happen 5 times like this. So what does that give us? There we go. Now I did kind of use another important skill on this one. I took the exponential form and changed it into repeated multiplication. So if we can do that, in addition to simplifying it into exponential form, then this, again, goes pretty smoothly. Okay. All right, simplifying this expression completely, there are rules for this. However, I hate the rules, even though we'll go over them. Okay. So what am I going to do? I'm going to take both of these, and I'm going to rewrite them both as the repeated multiplication. So that's what I mean. We're going to expand this, and then like water, contract it, right? Isn't that what Bruce Lee said? So this is z to the power of 4, z times itself 4 times. And yes, I do cross my z's so that they don't look like 2's. And then I've got another z to the power of 3, so that's z multiplied by itself 3 times. But these two were multiplied together in the beginning from this multiplication right there, right? So in reality, this is z repeated multiplication. So that's going to be our base, z. And how many z's were multiplied together? 1, 2, 3, 4, 5, 6, 7. Bam, z to the power of 7. And we did it. All right, what about this one? Well, I've got this b. It's just 1b. And it didn't show the exponent for this b, not because it usually doesn't when there's only one. But this is b multiplied by itself 1 time. Now that doesn't give us 2 b's, it's just 1b, all right? And generally, that's a phantom 1 though. Okay, so we have different forms of phantom 1s, which can be a little confusing. This is one of those cases. Then I've got b to the power of 2, that's 2 b's. And then over here, that's a lot of b's, but there's 9 of them multiplied together as well. All right, so there's all our b's, and all of these are being multiplied together, which means that we have one base, one value, that's being multiplied by itself repeatedly. And in this case, it appears that there are 12 of them. All right, so this does bring up the rule, which we're going to address right now. For example, that was a b to the power of 1 there at that leading multiple. If we were to look at the exponents though, right, because it's the same base that's multiplied over and over, what does it look like we did with those exponents?
Added them together.
That's right. Looks like we added them together. So it was really b to the power of 1 plus 2 plus 9, which still gives us the same answer right here, b to the power of 12. So this brings up the rule. X to the power of a times x to the power of b. Now once again we're multiplying x's repeatedly. But in this case, even with these letters as the exponents, we would just add these two together. So a plus b, and that is the rule. Right, so this, I don't know, we kind of look at this and it makes us feel bad inside. It's not really that bad though. We just have lots of different stuff. But it is all multiplication, which is good. For example, between these two parentheses is multiplication. So that first set of parentheses would be 3. Then I got 3 x's multiplied together. Then 5 y's. And then 6 z's. And this is all multiplied by the other set of parentheses, 4. And then 4 x's. And then 2 y's. Now all this is repeated multiplication. Just for this example, because we're kind of introducing this, I'm going to use the commutative property of multiplication to rearrange this so that terms that are similar are next to each other. For example, the 3 and the 4, those are both numbers, so I can move them closer together. That's 3 times 4. Next, I'm going to work on the x's. So I've got these 3 here. Yeah, we'll do it in a different color. These 3. 3 x's, and then over here 4 more x's. Next up, we'll look at the y's. So let's see, y's. I got these 5, and I got these 2. And then finally, we got these z's, all 6 of them. All right, so we're going to simplify this one group at a time. For example, 3 times 4 is 12. That's good. Next up, I've got these x's all multiplied together. How many of them do we have? 7. Next up, my base y's. How many of those do I have, excuse me, multiplied together? Well, it looks like 7 again. And then the z's. How many of these do I got? 6. So this represents the final answer. Now, that seemed like a lot of writing, I think it's better than memorizing the rule. However, we could have used the rule. We could have taken the 3 and 4 and multiplied them together to get the 12. The x's, I had 3 of them and 4 of them, so that's 3 plus 4, which ends up being 7. The y's, I had 5 of those and 2 of them, and 5 plus 2 is 7, which is shown down here. And then finally the z to the power of 6. There were no other z's to combine with it, so it just states z to the power of 6. Is that faster? Yeah. Is it easier? I don't know. That's what you have to decide. Because once we start getting more rules together, this may seem not so obvious. Okay. Simplify this expression completely. This quantity, negative 2, y to the power of 12, all to the power of 3. Okay. Well, that exponent, the 3, right here, it tells me how many negative 2 y to the power of 12s we have. All right, so I'm going to write that out 3 times. So this is what we really have. And we could rearrange this, which isn't completely necessary. What I can just do is take negative 2 times this negative 2 times this negative 2. And that would all combine to be negative 8. Now we got these y's. So in those other examples, I expanded these. But like I said, out of just convenience, we may use the rule, okay? Because I do not want to write out 36 y's. So I'm going to use the rule on this one. I got my base y, and I've got 12 of them here. I've got another 12 there, so I'm going to add those in, and this 12 as well. So my final answer ends up being negative 8, base y, 12 plus 12, sorry, that's supposed to be 12, plus 12 is 36. And this would be considered my final answer. So I'm going to do this one 2 ways. I'm going to do it the same way we did that last one. So I'm going to rewrite this 5 times, which may seem like a lot of writing, but again, it's okay for now. All right, there we go. I got that 5 times. So, well, let's see. Let's focus on this one base at a time. For example, these 5s right here. I got 5 of them, so that would be 5 to the power of 5. Then let's focus on the x's. So here's my x's, looking at all of them. And again, just out of convenience, we'll use the rule. X to the power of 7 plus 7 plus 7 plus 7 plus 7. There's 5 of those. So that'd be x to the power of 35. Next up are y's. So I've got y to the power of 1, 2, 3, 4, 5 4s added together. And then finally the z's. Oh, sorry, the y's. Let's simplify that. 4 plus 4 plus 4 plus 4 plus 4 is 20. Now the z's. Base z, 1, 2, 3, 4, 5 3s. So that ends up being z to the power of 15. Now, yes, and some of you guys see the rule already. And I guess we could kind of ask the question on this. Here are 5 7s, here is 5 4s, and here is 5 3s. Why is there 5 of each of them? Well, the answer is because we had an exponent of 5 here at the top. Okay, so that tells us we got 5 of each. So this is repeated addition, which we've already slightly discussed. And we could simplify that to be multiplication, right? That would be 7 times 5. And this would be y to the power of 4 times 5. And that'd be z to the power of 3 times 5. Again, those 5s come from this exponent from the original part problem. So we could look at this then. Let's get rid of that stuff. As kind of like we're distributing this 5 into the exponents of each of these multiples, except 5 again has an exponent of 1, and that's kind of where we run into trouble, at least I see on the tests, is that if we don't see an exponent, it's automatically an exponent of 1. So that would be 5 times 1, which was 5, and that's 5 to the power of 5, which is 3,125. So that becomes the rule then. When we see a base to a power, and that's in parentheses to some power, then we're going to take the same base, and we're going to multiply the two powers, m and p. Needs to be multiplied together. And again, it kind of works along with that last example. The p tells us how many groups of the m's we have, so we'll multiply the two together. As it turns out, the rule works with fractions, and I'm going to show you why here in a moment. So let's expand this then. I've got x to the power of 5 over y to the power of 8 5 times. And we're multiplying all these together, and that means that it's really just fraction multiplication, which means that all I'm going to do is multiply all the numerators together and all the denominators together. Well, we see that it's repeated multiplication over and over and over. So if we wanted to, we could use the rule on this and just add these exponents. And this will be divided by the y's. 8 of those, we're just going to add those together. And this gives us x to the power of 25 over y to the power of 40, which would be our final answer. Now that seemed like a lot of writing, so this is where the rule kind of comes in handy. If we look at this with the rule, I've got the 5, but with the fraction it's going to be distributed to both exponents, whether it's in the, let me rephrase that, it's distributed to all exponents in the numerator and denominator. So this one would have been x to the power of 5 times 5, all over y to the power of 8 times 5, which is what we got from this answer down here. And let's simplify this one completely. All right, let's use the rule then. If we're going to use the rule, though, let's acknowledge that that 5 has an exponent of 1, so that when I multiply the 3 into the exponents of these two bases in the fraction, then it's z to the power of 2 times 3, all over 5 to the power of 1 times 3, which gives us z to the power of 6 over 5 to the power of 3. Let's evaluate that 5 to the power of 3. I kind of assume that's what they want on the homework. Z to the power of 6 is not going to change. 5 to the power of 3, 125. I'm just going to address this right now, okay? With calculators, if I wanted 5 to the power of 3, the first button I would push is 5. This is for most calculators, by the way. But the second button, if you got a TI, it generally looks like this. And it's very close generally to the 7 or x squared button. Yeah, sometimes it looks like a y to the power of x button as well. Okay. Trying to think if it looks like anything else. Another one you may see. Oh, what the heck was it? I think. Yeah, this is generally on Casios. You'll see a box like this with an exponent box right there. So what that will do is you wouldn't need the 5 to begin with on this type of calculator. You would just push this button and then you fill in the base and then the exponent, which is kind of convenient. Oh yeah, so at the end of this, you're going to type in the power or the exponent, which is 3 in this case, and then you push equals. Then it will tell you that it's 125. For this one, I'm going to expand these because we haven't seen this stuff before. So even though it's a lot of writing, I got 12 z's in the numerator and 5 in the denominator. All right, so that's how it sets up. But this is, again, kind of like fraction division on this. And anything divided by itself is 1. So z divided by z is 1. But this z divided by z is 1. And yeah, the rest of them are 1s right there. As it turns out, we can change all of these 1s into phantom 1s. Because anything multiplied by 1 is itself. So what do we end up with? Well, I got a bunch of z's. How many of them do I got right here? 7? Rule, right? Well, if the last one was addition, of course, this one we can see, it's kind of like we took z's out from both of them. So we could look at this as z to the power of 12 minus the 5, because we subtracted the 5 from the denominator. And that would also give us the same answer, z to the power of 7. The quotient rule, in this format anyways, we have a base of a, it's the same, it does have to be the same base before we just subtract exponents. And this one would be, we got m and p, we would subtract these. Now it does have to be in this order. It's always the numerator exponent subtracting the denominator exponent. This brings up another question though, and we're not going to address it until just a moment, but if the denominator exponent is bigger than the numerator one, what type of exponent would we have? Be a negative exponent, okay? So just be aware that it is possible to have negative exponents, and that is coming. All right. Now this is kind of where we get to the point where the rules can kind of get mixed up. So for example, on this one, it is common for me to get answers on a test like this. Now this is mostly correct, but what's the mistake that happened right here? Yeah, the 6, right? How did they get the 6? They subtracted. So we get so used to subtracting the exponents that we feel like it's okay that we subtract the bases. No, that's not okay. So make sure that you avoid this mistake, all right? What we want to do is we kind of want to separate these. I don't know, that's not a fancy line, but it still works. I put that first one in the wrong spot, didn't I? They got me. There we go. All right, so this is actually 40 over 34. And I'm just going to simplify this as a fraction. So we'll divide both of these by, looks like 2. And that would give me 20/17. Now the x's. Well, I had x to the power of 10, and then x to the power of 7, so I'll subtract those. That's divided. So that would be x to the power of 3. Then the y's, y to the power of 20 minus 6, which would be y to the power of 14. Just so we understand this, because it does get confused sometimes, the x and the y bases are in the numerator as well. So maybe that's a little sloppy. So if I wanted to, I could write this as 20, x to the power of 3, y to the power of 14, all over 17. It means exactly the same thing. So, and you could kind of see that because using fraction multiplication, the denominators of the x and the y bases are 1. But once again, I'm okay with either of these answers. But sometimes the homework's picky. All right, we got this table. Well, good. Let's look at this. In this first box right here, so in this a to the power of 4 divided by a to the power of 7, I'm going to write this out because it's what it wants in the first column. So that's what this looks like. But once again, anything divided by itself is 1. So those kind of cancel out. And this ends up being over a to the power of 3 because we had those a's in the denominator. The question is what value goes in the top? Well, those purple ones are, well, they're 1s. So we could just say there's a 1 because anything multiplied by 1 is itself. So it's really 1 over a to the power of 3. Part of the problem with this, though, is that if we use the rule, then we would have had a to the power of 4 minus 7, which is a to the power of negative 3. Now notice that we did it's the same math, we just did it differently, and the answer is kind of shown differently. That's just so that we can see that a to the power of negative 3 is equal or is the same as 1 over a to the power of 3. These two mean exactly the same thing. It just depends on how they want us to express the answer. Generally, they're going to say stuff like, show the answer using positive exponents, which in this case would be the purple answer. and not the red one. But we'll have to be aware of that when we read the problems. So let's do that. A to the power of 3 times b to the power of 6 over a to the power of 6 times b to the power of 10. We're not going to worry about this last one. It's just, we'd have to use the rule, which is fine, but let's not worry about it, okay? So let's expand these. All right, so let's see what we can cancel out. I got 3 a's to cancel, 6 b's. So let's simplify this back into exponential form. So how many a's do I got left? Just these 3. A to the power of 3, and then these 4 b's. And again, we'd have to have a 1 in the numerator right there, okay? Because anything multiplied by 1 is itself, and those purple cancellations are 1s. Well, what does this mean on the other hand? Well, if I look at the original problem, if I use the rule on this, then I'd have a to the power of 3 minus 6, which is a to the power of negative 3. And then the b's, I would have b to the power of 6 minus 10, which is b to the power of negative 4. Well, this is the same as the value we just found. So this would be the same as 1 over a to the power of 3, b to the power of 4. So this negative exponent business that we're looking at, what it's really telling us is to reciprocate fractions. What does that mean? Well, it means that if I made these fractions, as soon as I reciprocate them, then it changes the exponents into positives. So reciprocating the fraction just means I'm going to flip it. And 1 times 1 is 1. 1 over a to the power of 3, b to the power of 4, which is what we get right here. Okay. So when we see negative exponents, the intention is to flip it as a fraction. If it's not shown as a fraction, we make it a fraction. If we were to see a problem like this one, so if I saw something like this, again, the negative exponent tells us to reciprocate this fraction. But when I do that, it makes the exponent positive. So we flipped it, right? And it made the exponent positive. That just makes this w to the power of 10. All right. So the rule then for this one, again, we would make that a fraction. And then the negative exponent tells us to reciprocate it and change the exponent to a positive. So that's the rule, which we've seen already. So if we wanted to show this with positive exponents, x to the power of negative 5, I'll make it a fraction and then reciprocate it and change the exponent to a positive. Done. Same idea here, write the expression with positive exponents and simplify as much as possible. So I'm going to make that fraction because it has a negative exponent, and reciprocating it gives me 1 over 6 to the power of 1. However, we don't really need to show an exponent of 1. So 1/6 is the final answer. All right, here's what happens a lot on this problem, all right? So we see the negative exponent, and we know to make it over 1, so we flip it, and we get 1 over 8 times y to the power of 7. Now this is partially correct, okay? The problem is, in the original problem right there, 8 has an exponent of positive 1. So it is not reciprocated. So if 8 has a power of positive 1, then it's just the y that has to be flipped on this one. So we still have 8 to the power of 1, but the y is flipped and made 1 over y to the power of 7. Now this is multiplication. It may be helpful to see that as 8 over 1, so we can see it's fraction multiplication. 8 times 1 is 8. 1 times y to the power of 7 is y to the power of 7. And that would be it. There it is. This is like the W one, right? So what's the answer to this one? That's correct. Just to have x to the power of 8. Is that okay? I mean, the negative exponent, again, reciprocated that fraction, and that's how we get that. So here's the nice thing is we got 2 negative exponents. They're already in a fraction, right? So that means that this y to the power of negative 4 is going to reciprocate to the top, and the x to the power of negative 7 is going to reciprocate down to the bottom. So I'm just reciprocating both of these terms because they both have negative exponents. But when I do that, it changes the exponents to positives. So x to the power of 4 over, that's a y, right? Over x to the power of 7. There we go. And that would be the final answer on that one. All right, if the bases were the same like this, we could reciprocate both of them like in that last problem. So x to the power of 6 over x to the power of 4, which would be x to the power of 6 minus 4, which is x to the power of 2. Or we could use the rule from the beginning, which would be negative 4 minus negative 6. Well, minus negative is the same as plus. And that gives us x to the power of 2 as well. So it works either way. All right, the rule for any exponent that is 0 for the base. Let's look at this in context, all right? So the question is, or it becomes, how do we get a power of 0? Well, it would be the same thing as taking 3 to the power of 2 over 3 to the power of 2. Using the rule, you'd get 3 to the power of 2 minus 2, which is 3 to the power of 0, right? But what does that mean? Well, it means you'd have 3 times 3 over 3 times 3. But everything cancels out as 1s, which means this is really just 1 times 1, which is 1. These are the same. 3 to the power of 0 is 1. But again, how do we get it? Well, it means that the exponents for both of these, the numerator and denominator, were the same, which really means we have the same thing divided by itself. And anything divided by itself is 1. So anything to the power of 0 is 1. And that is the rule. Now this is a very, very general way to look at it, okay? Sometimes the x right there is just some value or variable. Sometimes it's a huge expression. And those are the kinds that we like because we just want to see how close you're paying attention, okay? For example, this is what I mean, all right? Now we see this, right, and we kind of hate the way this looks. Well, not just because of my handwriting, because it looks kind of crappy, right? However, sometimes we put a 0 there on the outside of that, which means we're taking this whole quantity and raising it to the power of 0, which really means it's just 1, okay? So be careful. Sometimes we start, distributing stuff where we shouldn't anyways, or multiplying stuff together right there or right there, or canceling stuff we shouldn't in improper places. When in actuality, all we need to do is look at the exponent, which is 0, so we know the answer is 1. So like this one, 89 to the power of 0 is 1. Or this one, here's another set of parentheses to the power of 0. And anything to the power of 0 is, 1. Be careful because instinctively we may just want to put a 0 there. But it's not multiplying by 0, it's a power of 0, which is very different. All right, so there's the rules, kind of. Those last two we didn't really completely cover, but kind of did informally. So if you guys want to look at those and memorize them, again, I'm not a big rule guy, though, so if you guys like the rules, then that's good.